Hello everyone, my name is Thomas Johnson. I'm a lecturer or assistant professor in the Department of Biochemical Engineering at University College London. Today I'm going to talk to you about future-proof design for sustainable materials to enable purification of emergent biologics. We're going to start off this session by going through some learning objectives before talking about my motivation for performing research in this area and the results that we've generated over the past decade or so. I'll then discuss how we're going to use all of these results going forward into the next decade to meet emergent medical needs, before making some concluding comments and then wrapping back around into the learning objectives. So the first learning objective will be for you to learn, understand, also describe how imaging techniques are able to visualize and characterize materials. We're going to focus on bioprocessing and biomanufacturing structures today, but this is applicable to a large range of different materials that may be of interest to you. I then also want you to be able to discuss how structures in this space can be related to their function and performance, and how we can use these to compare between different materials and operational types in order to inform design of potentially new materials going into the future. Now, my motivation and interest for working within the medicines manufacturing space is that over the past few years, there's been a huge amount of exciting new therapeutic modalities passing through the clinic and onto the market. And these are able to treat previously incurable diseases, which is really fantastic. However, these new products also cost a huge amount to actually produce and also for the end user, which means that even if we can come up with exciting and very valuable cures for these diseases, ultimately it'll be challenging if we aren't able to afford these for all that need the medicines. And so a large contributor to these high prices that we're seeing for these new drugs is the manufacturing process itself. And so on the bottom left-hand corner, we have a simplified version of how we would manufacture various types of advanced medicines and biologics. We would start off in a bioreactor where we would grow cells, and either the cells themselves would be the product or they would create the products for us. My particular area of research and interest is in downstream bioprocessing, or the purification of that initial cell broth into the medicine itself that can be used in the patient. And typically, we'll see 10 or so unit operations in series. I've just simplified that down to 3 cartoon steps in this case. And all of these are complicated and rely on physical and chemical separation of high-value biologics in a chain in order to achieve the safety and efficacy of the final products that we require. And for a number of decades, we've been using this and optimizing this process successfully for monoclonal antibodies, or mAbs. However, with the new advent of these therapeutic modalities, which have different physical and chemical characteristics to mAbs, we're seeing that a number of challenges within the purification chain. And so if we take chromatography, which is the workhorse of downstream bioprocessing, and we compare the efficiency of viral vector manufacturing compared to monoclonal antibodies on the right-hand side as a very ballpark estimate in this case, we can see that as we try to bind this material to these columns, we can only bind 50 times less of these viral vectors at best compared to our conventional products. We're only getting half as much of our product out at the end of this unit operation, and rather than being able to use these columns 300 times, we can only use them 3 times or so before they have to be discarded, and they're over twice as expensive, which means that there's a huge amount of cost involved on top of this inefficiency during the manufacturing process just for this one step. So we're seeing that for these various types of consideration that we're looking at here, we're already losing orders of magnitude, which contributes to these very high prices. Therefore, what I think and what I'm really interested in is going back to the drawing board and looking at all of these new product types in terms of their physical and chemical attributes, and linking that to what specific types of structure are needed for the optimal and maximal separation, efficiency, and quality for the specific product and process that is needed, rather than relying on a series of established technologies, which we currently do. During the vision section, point 4 of this talk, I will then talk about 3 different areas I believe that in my lab that we'll be able to investigate and explore to achieve this. But first, we have to understand the current state of the art within this space. So packed bed chromatography, as I said, is a workhorse in the manufacturing of medicines. It's a cylinder which consists of a series of microspheres, about 50 micrometers in diameter or so, which are tightly packed into this cylindrical column. And these individual spheres also have an internal porosity as well, which allows us to get a lot more resolution in terms of our separation process, both on chemical and physical terms. For a number of decades, how we go about estimating our chromatography performance has been reliant on equation-based derivations and estimations, which can lead to some miscalculations when we're trying to work out how well these columns are performing. With the advent of 3D imaging techniques, predominantly X-ray computed tomography in this talk, and if you've ever had the misfortune of having to have a CAT scan at hospital, it works in a very similar manner. We're able to generate a 3D structure of these materials without having to actually cut through the samples themselves. And we can do this for the whole column to look at all of the individual particles or beads within that packed bed. And we can also apply that in a nanotomographic approach in order to see all of the individual pores within those spheres and all of the structures in between. And we can do that for a real sample of a real chromatography column that we can use for a real process. So that gives us a huge amount of power compared to relying on equation-based derivations to understand these structures. Not only that, we're also able to achieve this not only for static samples, but also how they change as they're used. Now, typically these chromatography columns are made out of reasonably soft materials such as agarose and cellulose. And so when we pass flow through these materials, we actually often compress them. And on the right-hand side, at the top, you can see a very small band where the chromatography beads originally would have been placed, but due to that live flow, we've actually changed the structure that a feed would actually experience. And again, we're able to visualize that and also characterize that, not only during an individual process, but also across the lifetime of these materials and how their structure changes and how that contributes to the degradation in their performance. Now, chromatography is extremely important for purification of high-value biological materials. However, there are a number of other unit operations which I'm just going to very quickly touch upon. A good example is depth filtration, which is used very early on in the process displayed on the screen. It has a very bird's nest-like structure, and this is really great for capturing those larger cells which we may no longer need and allowing our smaller product to pass through this structure. This complex structure is great for imaging, and in the bottom row we can see as we increase the quality of our resolution and also the quality of the imaging process itself during that resolution enhancement, we get far more detail out of these materials. And as with anything in life, the better you put in, the better you get out at the end. And in this case, it would be representative imaging data for us. Another important unit operation in downstream bioprocessing is flat sheet filtration, used for virus and sterile and bacterial removal within our process streams. We obviously don't want those when we're talking about medicines which may be injected into patients. In the center, we have a long rectangular grayscale image of what that filter structure looks like within those materials. And it's been deliberately designed to be asymmetric, which means that the pore structure gets tighter or the pores get smaller as we pass through that material from top to bottom. The example below that gives us a pore distribution map, which allows us to see the size, the shape, the connectivity of all of the pores within these materials of a real sample. And we can also characterize those pores as a function of distance through the material, which gives us a huge amount of information as to what the structure of these actual samples looks like. Now, this is all very well and good. However, what's really important is the interaction of that structure with the products and also impurities as they pass through these and getting trapped within these materials. On the top right-hand corner, we have a confocal microscope image, which has tagged a product or impurity that's passing through these flat sheets. As these products or impurities get retained, we can then identify in green where they are actually getting trapped. And so we can see a very thin, concentrated band across the center towards the top of this filter, and we can also see a degree of heterogeneity within those materials as well. So we can understand what the structure looks like and how that's impacting the filtration performance. And we can do this for a range of different operating conditions and different types of filter, giving us a far greater understanding of how does that structure influence the performance within our certain bioprocessing steps not shown here. And this work is currently being continued by Kwan and Hercules in my research group at UCL. So we can apply X-ray computed tomography and also other imaging techniques in order to better understand what these structures are and also how the products and our impurities are interacting with them. We then want to start to use that information as to how can we actually improve these materials we're using for our separations purposes so that we can actually improve the manufacturing process as a whole. And an area that I'm particularly interested in is ultra scaled down technologies. And this is where you're effectively miniaturizing the filtration process. In this case, it's a depth filter across the top row where we've got a small chamber containing that bird's nest structure. Once again, using an imaging process, we're able to see what this material actually looks like within that chamber. And it's very important that we eradicate any design issues at the ultra scale down level, because even though we've got the advantage of we're able to rapidly test and screen things at a smaller scale, and we're also minimizing the amount of material we're using during our testing, very important during when we're considering the high cost of these tests that we're running. Any issues that we have in the design process are going to be greatly exacerbated at this scale, so we really need to make sure that we improve our designs at this capsule level. Based upon this X-ray imaging and some CFD based upon this volume, so flow simulations, we're able to identify that there was quite a significant degree of bypass actually going around the filter. So obviously this is a major concern if we're actually talking about a filtration process, if we're actually getting a lot of the material going around the filter itself. Working with industrial collaborators, we're able to improve this design as a result using the same filter material by implementing a number of design changes. The two major ones were to include a drainage disc at the bottom, which gave better control over the flow behavior, and also some support for this reasonably soft structure. The second was to include a knife edge seal around the edge. You may see this on the bottom right image, just a small triangle that runs across the whole area, which compresses the outer zone, which prevents any flow from bypassing around the chamber. And we found, based upon particle experimental measurements, that we greatly decreased the bypass from the top design to the bottom design as a result, which is exactly what we wanted. And now we're continuing work in this space by, again, applying very high resolution imaging in order to investigate what that actual compression zone looks like and what are the changes to the flow as a result. And using this information, again, we can continue to consider what design decisions can we make to further increase the quality of our chamber. The next stage for us was to actually look at the separation material used itself and how can we enhance that. And a great example of this is some of the work performed by Dr. Simone Di Martino and his group at the University of Edinburgh. We teamed up to combine his 3D design and 3D printing of structures, which allows you to select the exact physical parameters that you actually want within these structures, with 3D imaging, because it's all well and good designing something which has perfect characteristics for your product and process of choice. However, if we're having challenges fabricating that or bringing that to reality, then we really need to make alterations. And so integrating 3D design and 3D printing with 3D imaging allowed us to do that. Again, across multiple length scales, from the whole gyroid or the whole 3D printed structure, all the way down to an individual unit, which can be considered to be similar to an individual sphere within the chromatography columns. And then an internal substructure which we create through some clever chemistry to create that internal nanoporosity, again giving us more surface area for physical and chemical separation. This imaging process, again, of real samples that have been 3D printed, allowed us to actually perform some flow simulations similar to the previous slide on real samples, so not just on the hypothetical digital constructs that we generated. And this allowed us to correlate between the two data sets, and we got very good results, which is very pleasing to us. In the bottom of this slide, you can see 4 pillars. And again, this is the individual units which are then connected. On the left-hand side, we have the image data set of one of these units, which makes up this whole gyroid structure. And on the right-hand side, we have this blue CAD volume, which hasn't been filled in. Again, comparing the digital design to the actual printed structure, we're able to then make an overlay for the whole material, not just an individual unit, and then identify, are there any areas where we need to improve either the design or make changes to the fabrication process to increase the fidelity of our printed gyroid structures. Again, this is very useful because otherwise you wouldn't know what one of these units looks like buried deep within these structures. Using this imaging approach, we're able to very easily get all of this data and make adjustments and improvements as a result. On the right-hand side, again, in a very similar manner to what we saw on 2 slides ago, we can identify the size of every single pore, its shape, its connectivity, and generate a pore size distribution in the bottom right-hand corner. This is very useful because then we can start to change the chemistry that we're applying within our 3D printing process to tailor that pore size distribution to the needs of our product and process. And Aprilia, again, in my group, is continuing that work at the moment. I also wanted to highlight a couple of other collaborations combining imaging with downstream bioprocessing that I have with leading academic institutions in the United States. One with RPI in Professor Kramer's group with Dr. Soni. We've been looking at where the products and impurities for an adeno-associated virus-based process are retained within those chromatography spheres. And we can do that for a series of different steps within the process to identify where the products and impurity are being trapped. Are they being removed as they should be? And again, on the left-hand side, we can compare and contrast that with the actual structure of these materials, which again have been specifically designed to have a larger pore size to accommodate larger products such as viral vectors. Some work with Dr. Stefano Menegatti at North Carolina State University uses imaging in a different capacity, in this case for screening of different ligands, which is the chemical binding and unbinding part of the purification process, to ensure that you get the best match between your binding and also what the chemical characteristics of your product is. And this is very, very important. And I think it's going to be fundamentally essential for us in the medicines manufacturing space, to consider how we can harmonize across all of these different length scales, from the chemistry at the ligand all the way up to what a capsule looks like and everything in between, to get the most out of these materials and recover some of those orders of magnitude we're missing from the earliest slides. And the bioprocessing space has a very strong research community, both across the UK, the US, Europe, and other areas as well. Just wanted to highlight some of the leading experts that I'm currently working with, not only in academia, but also it's very important to work with industrial partners such as Cytiva, who are a leading vendor in the bioprocessing space, in order to translate our research ideas into potentially commercially available products and really impact the real space within this bioprocessing sector. So hopefully that gives you an overview of understanding how we can apply high-resolution imaging techniques in order to visualize and characterize these materials, and how we started to apply that to designing new structures in this space. We also then, as a result, within my research group, over the next decade, really want to capitalize in this area for investigation. I'm going to talk about across 3 different areas which I think are going to be key for us to target going forward. The first is the consideration of the flow properties within these materials. And something that I think is particularly important is tortuosity, which is the effective flow path through these structures. If you have a straight line through a structure, it has a tortuosity of 1. If it has a slightly longer flow path, such as those on red on the right-hand side, it will have a tortuosity greater than 1. And that's going to be very important for both physical separation, but also chemical separation, because those flow paths will determine the opportunities for binding and unbinding of our products. And tortuosity is already an extremely important factor within chromatography. We have size exclusion as an example on the top right-hand corner. Take an example where we have a mixture of blue particles and orange particles. The orange particles are small, the blue particles are larger. Those larger blue particles have a tortuosity or a tortuous path where they have to traverse in the space between all of those spherical chromatography beads. However, the orange particles have that space to traverse on top of, because of they are smaller, they also enter the chromatography internal structure and have to traverse that path as well. That means that they have a greater tortuosity that they have to traverse when passing through these chromatography columns. So even without any chemical binding, they take a longer path, which means they take longer to get out of these columns. As a result, you can then separate out those two mixtures very nicely. So this is an area I think we really need to capitalize on going forward across all of these different length scales, because it really is a unifying factor in my opinion, and is something that's not particularly well understood at the moment. With the advent of 3D imaging techniques, this greatly enhances our capability not only to calculate the tortuosity factor, but also implement it as a design feature as well going forward. Something that's really going to be critical is enhancing the efficiency of our bioseparation processes. Again, going back to what products are being trapped within these materials or where they're being deliberately bound, we can see on the left-hand side with this sphere, they're all being bound to the very outside of this material. However, the surface area that's available is pretty much all inside of the actual structure, not just on the surface. So we're missing out on a lot of capability for separation within these structures, as evidenced with these images. Not only that, but because we're having to throw these materials away after only a few cycles, we're really not getting the most out of our structures. So in the future, I think we need to start to think about how we can enhance the efficiency of the materials we're actually using themselves. Not only that, but we also have to consider sustainability and various other environmental factors. Some of the structures that we look at, for example, depth filtration structures, are made up of multiple materials of construction. This can be cellulose, which obviously means chopping down trees, and also often contains perlite and or diatomaceous earth, which are very effective for separation purposes, for the capture of HCPs and DNA. However, they have to be mined from the ground from certain places in the world, and so these non-renewable, non-sustainable materials of construction then have to be shipped to wherever the depth filter material is being generated, and then has to probably be shipped again to wherever the medicine's manufacturing is happening. So there's a lot of inefficiency and sustainability concerns in this area, which I believe that we need to address alongside enhancing the efficiency of how we use these materials in the first place. And those two areas really combine into this final point of my vision, is that we need to really specifically tailor the physical and chemical needs of our emergent products towards the manufacturing and the structures that we're going to be using for manufacturing going forward, rather than just relying on a standard set of tools that we're making best fit. A lot of the factors that I've already spoken about, such as sustainability, identifying the product properties, and then linking that with the imaging to validate that the structures we're creating are fit for purpose, are really going to be important in incorporating, evolving, and augmenting this flowchart that I've displayed for you on this slide, just to give you an idea of the complexity involved in the design process. So, to conclude, we're living in a very exciting time in medicines manufacturing. There's a huge amount of new, exciting therapeutic modalities passing through the clinic and onto the market, which are ultimately changing lives and saving lives. However, their inherent complexity and the manufacturing costs associated with them are meaning that even if we can cure these very nasty diseases, we may not be able to afford to do so for all that need it. To address this issue, we need to go back to the drawing board and think about what are the exact structures needed for the purification and separation of high-value biologics, not only in the present but also in the future, so that we can drive down costs, increase safety, and increase the quality of the products that we'll be able to generate for generations to come. The way that I propose doing this is through three key areas, which link the structure, environment and sustainability, with specific design bespoke to the bioprocessing and the products that we're looking at the present and future time, to ensure that we can do the best manufacturing possible. Turning to the learning objectives, Hopefully now you should be able to have a better understanding and be able to describe how imaging techniques can be used to visualize and characterize materials, not only for bioprocessing, but if you're interested in other areas such as batteries, etc., how that could also be applied in those spaces as well. You should also be able to discuss how some of these structures can be related to their function and also their intended performance, and how we could start to think about generating a library of these different imaging data sets and compare across them in order to inform the design of our medicines manufacturing processes of the present and near future to meet clear medical unmet need and also demands going forward. With that, I will leave you with a series of references from my work, and I'll thank you for your attention. Thank you very much.